Before we get started with the newer material, is there any questions relating specifically to the material that was covered in the asynchronous lecture? Typically, people suggest that a lot of it was review, talking about the actin myosin filaments or like the sort of physiological structure of the muscle, and then the sliding filament theory about how the muscle contracts. And then we have the steps of muscle contraction. And then we talked about motor units. So how we have lower motor neurons that are connected to a certain number of muscle fibers, and that in itself creates one motor unit, a unit of motor contraction, and it is the activation of various motor units for an individual muscle that we are able to contract muscles by a certain degree. So action potentials are all or nothing in terms of a response, whereas muscles, they are able to be contracted by a percentage. So a lot or a little depending on the task that you're trying to perform. So no questions about any of that stuff, guys? That's awesome. Perfect. Okay, so when you guys give me the go-ahead, I will start on the newer material. All good? Okay, going once, going twice. Sold to Carolyn. She has started the lecture. So what we're going to do is first talk about motor unit properties. And this is probably a concept that you all have heard either in class or just in general life, this idea of different motor unit properties. So has anyone ever heard of like slow twitch versus fast twitch muscles? And so that's good that we've all thought about that or have heard about it. And it is the sort of fact that the different motor units in our muscles can have different characteristics. Now, we've heard of this idea of slow twitch versus fast twitch muscles, and it's dependent on sort of like this idea that the muscle fibers can have different sort of characteristics in terms of their twitch speed, their tension or the amount of force they can generate, and their endurance or fatigability. Now, the way that your body is sort of created, and remember the theme with the neurological system is that it's highly organized. And so the way that the motor units are organized is that, so if we have a given muscle, we know that for every given muscle, think of like the quadriceps, a big muscle, there are a large number of motor units. A motor unit is or represents one alpha motor neuron, and then the specific muscle fibers that it is attached to. And muscle fibers are only attached to one specific neuron. And there is a large number of motor units per muscle. Depending on the size of the muscle, you can have a large number of motor units. Now, the way that it's structured is that all of the fibers that are innervated by one motor unit are all of the same characteristics. So they all have the same muscle fiber composition. So depending on their variability in their twitch speed, their tension ability, and their fatigability, all of the muscle fibers in that given motor unit are physiologically identical. So when we talk about what would happen with changing the various characteristics of twitch speed, tension ability or contractibility, and endurance, we have our varying degrees of slow twitch versus fast twitch muscles. So here on this diagram, and just to confirm, you guys can see the cursor, correct? Perfect. Here we have just a generalized depiction of a varying degree of different twitch characteristics or muscle characteristics in different fiber types. So at the very far left in this diagram, we have an example of a fast twitch muscle. So typically when we have a fast twitch muscle, the twitch ability is very quick, and that generates a high amount of force. The problem with very forceful and fast twitch muscles is that the fatigability of the muscle is increased. So it has a very low endurance. And we can see that in this diagram here. So here we have a depiction of the force of the muscle, and it generates a high amount of force in a low amount of time. However, if we look at the rate of fatigue of this muscle, so our fast twitch muscles, it generally loses its ability to contract or generate force in about 2 minutes. So the endurance of our high force muscles or high force fibers is very low. Whereas on the very far right of the spectrum, we have an example of a slow twitch fiber or an endurance-based muscle fiber, where we have it contracting. It takes a very long time to contract. It generates low tension. However, look at the endurance of this muscle. It's greater than an hour. Now, originally, when exercise physiologists were first starting to look at muscles, they would classify them as either slow twitch or fast twitch. And through science and over the decades, they've realized that it's sort of a gradient or a spectrum, that it's not just one or the other. There's like a stepwise difference in the muscle characteristics. At the very far left, having fast twitch, and at the very far right, having slow twitch. So now we have a large number of different muscle fiber types, all sort of classified by different naming systems. So it's not just slow twitch or fast twitch. We have type 1. Type 2 is generally described as a fast twitch muscle, but there's varying characteristics within the subclassifications. Type 1 would be our traditional slow twitch muscles. So when we think about slow twitch versus fast twitch, does you guys know the difference between red meat and dark meat in chicken? I know it sounds kind of gross, but white meat would be fast twitch muscle because it's dependent on muscle glycogen, whereas red meat is slow twitch because it's dependent on aerobic activity, so blood, so it's dark. Now, this question is always brought up in lectures. So what about like once you, so let's say we have, a number of motor units for a given muscle. Now, can we train, like is that set in stone, or can we train muscles to have a higher composition of fast twitch or a higher composition of slow twitch? And the answer is, of course we can. And that's through exercising or different training regimes. So an example with, is there any runners, any like endurance athletes where you get like big muscles? And that's because you're increasing the amount of aerobic or type 1 fibers in that particular muscle. Someone that walks a lot has really big calves, whereas think about a basketball player or a high jumper. They have very lean, very thin, strong calves. And that's because they have an increase in the number of, for all the given motor units in that muscle that we're talking about, there is a higher now percentage of fast twitch versus slow twitch. So for exercises or activities that would require endurance, you would have more slow twitch. For things that generally require burst, like jumping or burst activities, like sprinting, for example, you have a higher percentage of fast twitch. So when we talk about this idea of plyometrics, where you're increasing, the idea of, does anyone know what plyometrics is? Plyometrics was sort of like an exercise program that was developed for different sports to increase like jumping speed, or it's just to increase fast twitch composition in a particular muscle. And so what you're doing is with training, what's happening is that by using the way that you activate the muscles, what happens is that proteins and like different proteins are being transcribed just as a result of training that takes muscles fibers and converts them more to generate more fast and faster twitch. So it's a sort of like a progression. So with time, you get muscle fibers that are sort of becoming more fast twitch versus slow twitch, and that's how the sort of training works. Does that make sense to everyone? Okay, perfect. Good. No questions? All right, let's continue on. So remember I was saying that when we're talking about an action potential, so the functional unit of the neurological system is the neuron. that the neuron, when it generates an action potential as a result of a buildup of local potentials, to bring that neuron to threshold stimulus, you get an all or none response that is an action potential down the axon of that particular neuron. It's an all or none response. Once it starts, there's no stopping it. Now, therefore, a single motor unit can't generate like 50% contraction. And I was saying at the beginning of the lecture that the ability of a muscle to contract a little bit or a lot is not going to be based on the sort of gradation of the amount of a motor unit, because it's an all-in-one response. The way that we are able to contract muscles by a varying percentage is through motor unit recruitment strategies. So if you want to a muscle to contract at maximum, you contract 100% of the motor units, or you fire 100% of the motor units. If you want to contract the muscle by 50%, you contract or you activate 50% of the motor units. So it's through the selective activation of a number of motor units that we're able to change the percentage by which we activate our muscles. Does that make sense? Perfect. And so because everything is organized in the neurological system, the way that we selectively choose different motor units when we contract our muscles by a certain amount follows specific strategies, and that those are through what we call motor unit recruitment strategies. Here we have an example of what the force in relation to the activation of one motor unit would look like. So here we have time on the x-axis and then the amount of force on the y-axis. And this looks similarly like the change in electrical potential that we saw with the activation of an action potential. With a motor unit, if it turns on, we get a contraction of the muscle, of that muscle fiber, and then it relaxes, and then it goes down to baseline. So it's a single hump. So it's an all or none response. The patterns at which we selectively choose motor units to increase the amount of force in a given muscle is through two different strategies. The first one is you increase the number of motor units to increase the amount of force that a muscle can generate, where you have maximum at 100%, a maximum at 100% of force, you have recruitment of all of the motor units, where you have with lesser amount of contraction, you are activating less than the maximum amount of motor units. So the first way to increase the amount of force that a muscle is generating by is you increase the number of motor units that you're activating. Now, what happens if you activate all of the motor units and you still want to increase force? Now, what we saw with the temporal summation of our local potentials on the dendrites, the same sort of thing can be said of the muscle contraction strategies. If you've activated all of the motor units, you can still increase the amount of force that the muscle can generate by increasing the frequency of motor unit discharge. So what you have is would have the just like summation of the action or the local potentials. You have a stepwise addition or summation of the force of the muscle fibers contracting. Now, Matt asks, what about the latent period? Now, the latent period is the time where the muscle relaxes. Now, when you contract a muscle, not all motor units are activating at the same time. So when we're going to look at EMG, it's all cyclical. So they're all kind of like going like certain fibers are contracting at one time and other fibers are contracting at another time. So it's not all at the same time. And so you can have a buildup of the force because you just increase the frequency of motor unit discharge. So if I show you a diagram here, let's see here. I'm just skipping ahead a little bit, but do you see how when you're looking at the electrical activity of a muscle, it's not just like one like solid bar. This is muscle activity. So this is the electrical activity of a muscle, and this is the force that it's generating. When we generate force in a muscle, it's through the activation of our motor units, but our motor units all don't activate at the same time. We selectively activate them cyclically. So that way they're not all activating at the same time, and so the forces can build up on each other. If we didn't do that, then muscles would just contract all at the same time and then relax. So if that means that we don't selectively activate motor units at the same time, how do we choose the order in which we would like stepwise activate them? And you guys may have heard this before, but have you guys have heard Henneman's size principle? So Henneman's size principle is basically the principle that we selectively activate our motor units in an order based on size. So let's say we had, so Zafir has not heard about that. So Henneman was just a scientist that sort of figured it out, but we have a larger number, we have several motor units for a given muscle. The way that we choose the order in which we selectively activate them over time when we contract a muscle is through the order of size. So we activate the smallest motor units first, and then we selectively increase the ones we activate based on the size principle. So the next biggest, then we activate that one. The next biggest, then we activate that one. We just sort of continue on in that way. And the reason why your body does that is because the smaller muscle fibers are the slow twitch or the endurance-based ones. So if we were going to contract a muscle, the body doesn't know how long we're going to be contracting that for if it's a voluntary contraction. And so it will selectively activate the most endurance ones first. So that way, on the off chance that that contraction is going to hold for a long amount of time, the ones that are selectively activated first are the ones with the most endurance. And then the other way, or the other reason why your body would do that is because if you stepwise activate muscle fibers with the next biggest, then the amount, like, so when you contract your muscle by more and more of an amount, it's a very like fluid sort of contraction. If you like pick small muscle fiber, then big muscle fiber, then medium, then big, then small, like when you contracted a muscle by more and more of an amount, it would be like jerky. So by adding muscle or as muscle fibers or motor units in a stepwise fashion, like or selectively activating the next biggest one, you're allowing for a smooth activation of the muscle. And so Jacob asks, is it smallest biggest? And yes. Remember, smallest ones are the slow twitch. So they're the endurance-based ones, whereas the biggest are the fast twitch, high contraction force ones. Yep, there is a refractory period for motor units. However, we're not activating all of them at the same time. So they're always building on each other. So then think about the larger number of motor units that are in a given muscle. They're not all contracting at the same time. So there's, in any given period, some are off and some are on. And so with a higher contraction, you're just cyclically activating more and more motor units. So for a 20% contraction, you're activating a certain number of motor units and they're cyclically turning on and off, on and off, on and off. Whereas for a higher contraction, you are recruiting a larger number of motor units, and so the larger number are cyclically turning on and off, on and off, on and off. Does that make sense, Avery? Perfect. Hopefully that all makes sense to you guys. Because, and then you guys are all right, like there's a refractory period associated with these muscle fibers. But remember, with the sliding filament theory, it's like a cyclical process, it's like a bike. It looks like we're just contracting, but what's going on, like I'm holding, what's going on the inside is a cyclical contraction, release, contraction, release, contraction, release. And then, so this is just a diagram depicting Henneman's size principle. And then this is an example, and we'll talk about research in a little bit, talking about what it would look like when we use EMG or a recording device to measure muscle contraction. And so what we do is when we use EMG, we're looking at the electrical activity that's being built up in a muscle. And so remember that to activate our muscle, we're using motor units, which is a nerve. So you see electrical potentials. And what we see when we record them is that for larger amounts of contraction, we have more electrical activity because you're activating more motor units. And what you notice is that it's not just like one bump. Look at all the little blips. Like it's where we're activating motor units off and on, off and on, off and on cyclically. Now, given the refractory period of our muscles, if you were to look at a single muscle fiber, just like our local potentials, if there is a, so let's say the muscle fiber is reactivated before the tension in the muscle fiber dissipates totally, there's a summation of the force, just like with the local potentials. So here, in this diagram, we have an example of how you can also increase motor unit, muscle contraction by increasing the frequency of motor unit discharge. So in this diagram here, at the very, very left, we would have one action potential in a motor unit, and that would give us our like typical muscle fiber contractibility graph or line. So you see that there's an increase in force, and then there's like sort of a decrease, and there's a refractory period. Whereas if you have two in a row, so given the refractory period of a neuron, remember you can reactivate it, right? Like you can, once the absolute refractory period is over in a neuron, it can have another action potential. So in this case, we have two action potentials of the same motor unit in a row. And then the second action potential causes contraction of that muscle fiber before the force that had been generated from the initial contraction is completely dissipated. So there's a summation of that force. And so if you continue to fire the motor unit before the force dissipates, you get an addition or a summation of the force. And if you do it fast enough, you get what's called a fused tetanus, where everything sort of builds up to max. Does everyone understand that? Okay. So studies have looked at like sort of the frequency that's required or the frequency that is involved in generating sort of a fused tetanus when looking at motor unit firing and muscle contraction. And so here we can see with wave summation, so this is less than 20 action potentials per second, or a frequency of lower than 20 hertz. You can see that there's only a small addition of the motor unit contracting force with each successive action potential. Whereas if you get to a muscle motor unit firing frequency of 20 to 30 stimuli per second, so 20 to 30 hertz, that's when it starts to build up. And that's called an unfused tetanus, like we saw in the previous diagram. And then to get to a point where we have a smooth contraction or a fused tetanus or a stable contraction of the muscle, we need to fire our motor units at a frequency of about 80 to 100 hertz. And so don't worry too much about the numbers. I just wanted to put this slide in to sort of like to show you guys that it happens so quickly. Like the refractory period, what's happening here is that the same motor unit is firing at a frequency of 80 to 100 times per second. The whole thing happens so quickly. Interesting, right? No comment on that one, so maybe not interesting. Okay. So this whole idea of increasing the contraction of a muscle by increasing the motor unit firing frequency, that's called rate coding. So the two ways that we increase the number or the amount that a muscle is contracting by is by motor recruitment or recruiting more motor units, or rate coding or increasing the firing frequency of those motor units. And the recruitment strategy that the muscle will use is going to be based on muscle size. So think of our like dorsal interosseous or our finger muscles, or even the muscles in our eyelids, like the ones that blink or move our eyes. Like they're not very big. So because they're very, very small, like in terms of thickness, there's not a lot of motor units that you can have because there's not a lot of muscle fibers. So muscles that are small, they have to rely more on rate coding or firing frequency because very quickly they recruit all of the motor units because there's not that many muscle fibers or motor units. Whereas larger muscles like our quads and our calves and our biceps, they rely more on motor recruitment because there is a larger number of motor units that are available based on like the thickness of the muscle. Does that make sense, everyone? Because the question is that, well, if you have a given muscle, why do some rely more on firing frequency versus on recruitment? And it's basically based on the fact of size, whereas bigger muscles have more motor units. Is everyone okay with that? Awesome. Maddie says yes. Okay, so this chart here is just depicting exactly what I had said. So if we can all look at this diagram, here we have the amount of contraction, the amount of contraction for a given muscle. So 0% to 100%. And then on the x-axis, we have, oh, sorry, I screwed that up. On the y-axis, we have the percentage of the motor units that are being recruited. Whereas on the x-axis, we have the percentage of the amount of force generated in a muscle. So we have a quad, we're flexing our quad by 0 to 100%. And then this is the percentage of the amount of motor units that are being activated for that given muscle. And what this sort of chart or diagram is meant to sort of describe is the difference between small muscles versus big muscles. So in blue, we have a small muscle. Let's say it's the first dorsal interossei. So it's a finger muscle, very, very small. So at 100% of motor unit recruitment, because it's so small, you're only at 50% of the contractibility or force generation ability of that muscle. So it relies more on rate coding of taking whatever motor units are there, the small amount of them, and then increasing the frequency of discharge. And so we get 50% more contraction ability through increasing the frequency of firing of those motor units for that small muscle. Whereas the difference with a large muscle, let's say it's the quad, you can see that 100% recruitment of all of its motor units, it's at about 90% of force generation ability. So the last 10% is going to be based on rate coding. Are you guys okay with that? So this is just, again, stating the same fact, but just sort of like in a visual. Everyone okay? Perfect. Am I going too fast? Is everyone good? Okay. And so the last couple slides on this particular topic that I want to talk about was just this whole idea of EMG. Reading the amount of contractibility in a specific muscle based on the excitation of a motor unit is called a myogram. So you can look at like one fiber and then you generate an action potential. So here's the action potential that's generated, and it is associated with a generation of a particular amount of force. This is called a muscle or a myogram. Whereas in our lab, so in the research that we had done, we utilize EMG. And so it's using these electrodes. And so that's the first finger muscle. And you're using the electrodes to look at the amount of electrical activity that's being generated in the muscle. And that's going to depict or sort of give you an idea of how much the muscle is contracting by, because you are looking at the amount of electrical activity. And we know when you activate muscle activity more, so that means there's more of a muscle contraction because you're increasing the number of motor units that are being utilized or recruited. So if you compare the EMG in a muscle, so this is the electrical activity that would be sort of recorded. And then so like, remember the picture where that so this would be the recording. The green is the recording of the muscle activity, whereas there's probably like a force transducer on the person's finger. And so that is measuring the amount of force that the finger is generating. So I have a question from Jacob. He says, when someone does a test for their force when jumping, what machine is typically used? So, utilizing EMG dynamically is very difficult because you have to time everything. Typically, what they do is they look at, they have electrodes attached to the person's skin and then on a battery pack. And then what's measuring the force is going to be a force plate. So that way they don't need to have another set of equipment on top of them because they already have something attached to them. They're going to jump onto a plate that measures the amount of force that the person's feet are generating. And then using the two in physics, you can kind of figure it out. Yeah, good question. Awesome. So is there any questions about that in particular? So just to give you guys a background, and so in my research, we were looking at sort of the activation of the rotator cuff in different positions. So we were funded by the automobile insurance company and companies, sorry, and they wanted to look at why the workers in the automotive industry were getting injured when they're doing some were getting injured doing arm tasks or some weren't. So what was the biggest difference in those jobs that are very risky to get hurt, whereas jobs that are not? Because looking at it from the outside, they were both doing similar motions with their arms. And the problem that we figured out was that when you have increased gripping, it increases the amount of force generated by the rotator cuff. And we utilized that, or we figured that out through EMG. There was higher rotator cuff EMG with gripping versus not gripping. So the key factor that was sort of the difference in people that were injured versus not injured, or the risk of injury, is the fact that those that were getting injured required an increased amount of gripping, which probably generates more force and requires more stability in the shoulder. Okay. So now let's continue on with spinal cord and reflexes. No questions? Anyone? No question? Going once, going twice. Okay. No questions. Awesome. So now let's talk about sort of the neurological path, right? We talked about the lower motor neurons, and so how recruiting the amount of those can generate force when attached to the muscle. Now, what happens is that those lower motor neurons, they are starting off in the spinal cord. And the spinal cord itself can, sorry, they're talking outside. The spinal cord itself is, give me 1 second. Shut up! Shut up! It's all good. All the lower motor neurons to our muscles, they start off in our spinal cord, right? So the spinal cord itself, through reflexes, is also capable in sort of helping out with movement, right? When we think about the neurological system and the primary motor cortex, it's a lot of information. So if we had to voluntarily figure out how to contract every muscle, it would be too much processing for the brain to perform the intricate movements that we're able to perform. So the way that the neurological system deals with that is that we have a lot of coordination that occurs through the spinal cord when the upper motor neurons, or when the exponentials go through the upper motor neuron tracts down to the lower motor neurons. There's a lot of coordination that occurs in the spinal cord through reflexes. And that what that does is reflexes they're not sort of like a computer, it's just a reflex, right? It's done automatically. It decreases the amount that our brain has to control our muscles. So remember, we're going to talk about how we have our tracks that connect our motor planning areas to our muscles. So when we talked about the somatosensory system, do you guys remember for the dorsal column and the spinal thalamic tract that there was how many neurons to get from the receptor up to the brain? Yeah, exactly. Matt said 3. In the motor system, there's 2. there is going to be the upper motor neuron that goes from the brain to the spinal cord. And then there's the lower motor neuron that goes from the spinal cord out to the muscle. So when we talk about the lower motor neurons, they're going to begin in the spinal cord, so in the gray matter, and then you're going to connect based on the motor unit to an individual muscle and its specific muscle fibers. The lower motor neurons can be classified into two different types. The alpha motor neuron, so this is going from the gray matter of the spinal cord out to the muscles fibers specifically, whereas the gamma motor neurons are going to be going to the proprioceptors of the muscle spindles. So they're going from the spinal cord out to the muscle spindles of a particular muscle fiber. Do you guys remember alpha gamma coactivation from the previous lecture? Muscle spindles are heavily the most important in terms of proprioception, but they need to be tight to register length or rate of change of length in the muscle. So when we contract our muscles, we also have to contract our muscle spindles. So when we contract our muscles, you also have to, at the same time, contract the muscle spindles of that muscle. And that's achieved through alpha gamma coactivation. The muscle spindles can contract. They're going to be attached to gamma motor neurons. The muscle fibers, or motor units, are going to be attached by alpha motor neurons. And so the alpha and gamma motor neurons run together. So your brain doesn't have to actively contract them. Just when the upper motor neuron goes to the spinal cord and goes out to the muscle via the lower motor neuron, the alpha and gamma motor neurons run in parallel. So that at any given time, if you flex a muscle, you're also flexing the muscle spindles, and therefore your muscle can register the rate of change of length or length change at any given time. Does that make sense, Antonius? Yeah, everyone's good with that? So here's an example of, so we have two different types of lower motor neurons, but it's not controlled by the brain. It's just a reflex in the spinal cord. If you activate one, you have to at the same time activate the other. So you have an interneuron that makes sure that the action potential goes to both, and then it goes. Awesome. Now, the way that our lower motor neurons are sort of grouped together is in what's called myotomes. So can we all see this sort of diagram here? So this is an example of the spinal cord. So this is depicting the spinal cord. Here we have the gray matter. This is the back end, so this is white matter. So this would be our dorsal column. Spinal thalamic tract would be here. So this is all sensory. The anterior part is all motor. So in the gray matter, which is where the cell bodies or the beginning of our lower motor neurons would be starting, is all located in the anterior part of the gray matter. And the way that they're sort of grouped together is in lower motor neuron pools. A myotome is defined as the groups of muscles that are innervated by a particular spinal nerve. So has anyone ever heard the term dermatome? We talked about dermatome last day, I think, right? So a dermatome is the amount of skin that is going to be sort of innervated by one spinal nerve, so L1, L2, L3. A myotome would be the individual muscles that are innervated by a particular spinal nerve. But what I want you to get from this diagram is that the way that the cell bodies of a particular muscle are grouped together for a given muscle is in what's called a lower motor neuron pool. So this is how we have all of the motor units. So all of the alpha and gamma motor neurons to a specific muscle, they're all grouped together in these groups. So all very, very close together. So this would be, like, so let's say this is the upper limb. So here we have pec, deltoid, pec minor, lat. This would be lower, serratus anterior. They're all of the cell bodies, so all of the neurons in a specific motor neuron pool that go to a particular muscle are all grouped together. Because remember, the key of the neurological system is organization. What I wanted you to get also out of this diagram is that, look how, like, so for bigger muscle, more motor units, the lower motor neuron pool, or the size of the pool would be bigger for a bigger muscle, right? It's just more neurons. So for big muscles, like look at this one here. See how we have, let's say this is like a really big muscle. Let's say our pec major, hypothetically. Can you see how the grouping of neurons in this motor neuron pool goes out from 2 different spinal nerves? So there's an interlap of, so you can have the pec that exits through a multiple number of spinal nerves. The way that it's organized based on size isn't just that, like, pec comes out of T2, lat comes out of T1. It's not organized that way because the muscles are so big that it has to exit through multiple levels of the vertebra. Is everyone okay with that? Not COVID, promise. Everyone's good? What are the numbers today? Yo, COVID ruined Halloween. Okay, let's continue on. Okay, so we talked about the lower motor neuron pool. Everyone is good with understanding what lower motor neuron pool is. So the collection of the cell bodies for a particular muscle are all grouped together. The way that they're organized sort of anterior posteriorly in the gray matter is also very organized. And we brought this up in the asynchronous lecture, but the lower motor neuron pools are correlated to anatomical position. So we have medially in the gray matter, we have our axial and proximal muscles. So the muscles that are more medial to us, whereas distal muscles like the finger muscles would be located more laterally. Flexor muscles are located posteriorly, where our extensor muscles are located more anteriorly in the gray matter. And so, not an acronym, but sort of a visual depiction that helps us sort of visualize that is like this. So you imagine like 2 arms flexing in the gray matter. And that kind of reminds you that, okay, proximal muscles are located medially, distal muscles are located laterally in the gray matter, extensor muscles are located anteriorly, and flexor muscles are located posteriorly. No, yep. So axial means anything like within the body, whereas like distal is like out. So medial or axial, distal, distal. Yeah. Is that okay, guys? So now you understand how sort of everything is grouped together, right? Very heavily organized. And then a lot of this research wanted to look at, like, so if you get a disc herniation here, or let's say you get like an injection or an infection here, it's going to affect certain muscle groups, and you can make an idea based on sort of where it is in the spinal cord, and then where it is like sort of like horizontally, anteriorly. You get a better idea of how everything is situated, right? We talked about white matter represents the tracks, right? So then you know that this is all sensory, and then we're talking about, at the end of lecture today, we're talking about the tracks that are in the anterior white matter, so the motor tracks. The lower motor neurons aren't tracks, they're going out to the muscles, so their cell bodies are located in the gray matter. Okay. So when we talked about the spinal cord, and I had mentioned that like with alpha gamma coactivation, it's a reflex and it decreases the amount of processing that's required in the brain. There are other types of reflexes that are required for the coordination of our movement that are located in the spinal cord. They're all through inner neurons, and it again decreases the amount of processing power that our brain already has to do. So the first one is reciprocal inhibition. So that's an example of a reflex. And what happens is that when we activate a muscle, reflexively we inactivate the antagonist muscle. So if I flex my bicep, a reflex, so if I send my signal out because I want to flex my bicep, I automatically turn off my tricep. Because if that didn't happen, we're going to talk about the stretch reflex. You know when you get a tendon tap reflex at the doctor? You tap a muscle or you pull on a muscle, it fights back. If I didn't turn off my tricep when I flex my bicep, my tricep would reflexively turn on. So then I'd be stuck. So rather than your brain say, okay, I want to turn on my bicep, also turn off your tricep, this reflex, reciprocal inhibition, just means that when you flex a muscle, the brain says bicep go on, it automatically in your spinal cord sends out a signal to your tricep, turn off. And that's true of all muscles. That's called reciprocal inhibition, and it's important with voluntary movement to prevent the stretch reflex in our opposite or antagonist muscles. So Apollo says, so does that mean you get it or you don't get it? Oh, you got it. So it's an aha moment. Got it. Very good. You're welcome. Another concept is that, remember when we talked about our spinocerebellar tracts where we have all of the proprioceptive information going up to the brain? You guys remember that? All of the proprioceptive information from our muscle spindles and our Golgi organs and all of the proprioceptors in our muscles, they get put into the spinal cord and in interneurons. You get the spinal cord is always aware of what muscles are flexing, and also because all that information is going in and coming down, right? All that information is getting put into the spinal cord. All of the proprioceptive information goes into the spinal cord first before it goes up to the cerebellum, right? Or and then up to the brain. So what we say is that the spinal cord has a proprioceptive body schema for any given muscle in real time. So this is an example that I always do in class, but obviously we're not in class. So what I would get is I would get someone to come in, and I would get them to hold my arm, right? You get them to flex, and then they let go at a specific time, and then my arm automatically flies back. Do you guys remember that? You guys ever tried that? You know, you hold someone's, you get someone to pull in front of their face, and then you pull against their arm, and then you let go, and they hit themselves. Okay, let's see. You guys have never done that? Hey, Ambreen, can I borrow you? I have to demonstrate something. Okay. You guys can see it. Excited?
I'm set.
Yeah. So then this is not the PNF stuff. This is okay. So then, can you guys see her arm? Okay. So I'm gonna get her. You do against me because I have something to face. Okay. So you're gonna hold my arm.
Okay.
With as much force as you can. So I'm holding myself. I'm flexing against her, and then don't tell me when, but any given moments, let go.
Okay. Are you sure?
Yeah. You guys see that? Because what's happening is that
Jacob didn't see. We need to do it again.
No, that's before. Oh, Jacob, eh? Jacob wants me to get a bruise. Okay, so at any given time, I'm flexing, and so all of that proprioceptive information is going into my spinal cord, and it's adjusting by how much each of the muscles that I'm contracting are flexing by. And so it's as a result of the reflexes of the proprioceptive information that's coming in, automatically it adjusts the amount that each muscle is contracting by. They wanted to do the other way around.
Who the heck is Apollo?
Yeah, Apollo, I like it.
What did I do to you?
Jeez, Apollo. She's the kin grad from Ontario Tech. You want that to happen?
Yeah.
Okay. Oh, yeah. Okay. Yeah, I'll continue on, and then I'll come grab you. Actually, you want to stay for a second?
Yeah, sure.
Okay. So, at any given time, you have all of the proprioceptive information going into your spinal cord, and then it's dispersed through interneurons to the various areas that it needs to go. So it can go back and adjust the frequency or firing of muscles in like distally, or it can go up to the brain to the cerebellum through the spinocerebellar tracts, or it goes up to like conscious perception through the somatosensory system. So there's always a real-time amount of information, and that's called proprioceptive body schema. And then the way that it adjusts the activation of the different sort of agonist muscles for a given movement is called muscle synergies. So let's say you were walking, let's say you're walking and you get, I'm trying to think of an example. So let's say you're learning to walk with a cast. So you sprain your ankle and you are put in a walking boot. Do you have to relearn to walk, or you just kind of like just start going? You already know the motion, and so you're going to try to activate it in the same way that you've already learned. If certain muscles aren't available, automatically what will happen is that the muscles that are available will just like change the percentage that they're contracted by via proprioceptive information. This muscle is not available, the other ones will start to like upregulate. So that's again another example of how your brain doesn't have to process it, because it's already doing so much. This is just another way that the spinal cord contributes to coordination by adjusting the frequency or the firing or the contractibility of our different muscles to varying degrees based on proprioceptive information. Okay. The next one, are you guys okay with that? So you just need to know them very briefly. The idea is just, again, I'm trying to highlight the fact that the spinal cord and these activation of our lower motor neurons is also through reflexes, through spinal cord coordination. And what that does is it decreases the amount of our brain processing that is required. So here we have an example of proprioceptive neurofacilitation. Does anyone know what PNF stretching is? Okay, so so the actual reflex that's called is called autogenic inhibition. Oh. I'm gonna get and bring it on the table here. So I'm going to demonstrate it. Okay. So autogenic inhibition is a way that we can get muscles to stretch. And so what happens with autogenic inhibition is that, you can see here. So with autogenic inhibition, what we have is we have tension. If there's too much tension in a muscle, any given muscle, reflexively, the muscle will turn off to prevent it from tearing. So what we do with people, and this is an example of like tight hamstrings, for example, lie on your back for me. What I'm going to do is, can you guys see her like? Okay. So this is, I'll give a good hamstring.
I do?
Yeah. Okay, so this is the end of like her range of motion, and then you feel it in your hamstring?
Yeah.
Okay, so with autogenic inhibition, if there's too much tension in the muscle, and that's regulated through the Golgi tendon organs of the tendons in a given muscle, in this case we're talking about the hamstrings, probably the calves a little bit. If too much force is generated, reflexively that signal is going to get sent to the spinal cord, and then there's going to be an inhibition of that muscle, autogenic inhibition. And so it's a way to our reflexes prevent our muscles from being overstretched or tearing. So what we do in rehab is we can use this mechanism to increase the amount of range of motion in the muscle. So that's probably the end range right there. Mm-hmm. So what I'm going to get her to do is I'm going to get her to push or flex the muscle that's implicated, in this case the hamstring. So flex her hamstring, and I'm resisting her. She's pushing, and then let go. See her leg just went up? That's because there's a moment through autogenic inhibition that the muscle turned off. Now go again, push. You okay? Yeah. And let go. See how it goes again? Like, so I just increased her range of motion through a reflex by like 15%. One more time, okay?
Okay.
And let go. See? And you keep going. You okay?
Yeah, okay.
Okay. So if everyone can do a, that was an example of autogenic inhibition. Everyone give her a virtual clap. I don't know how to do that. Claps. Clap, clap, clap. Yay! Oh my God, give it likes. Give it likes. Yeah, now you're gonna sign. Yeah.
Wait, what?
I don't know. Likes.
Oh.
Okay. Awesome.
Am I needed still?
Nope, you're good. Thanks, Emery.
Do you want your coffee?
Yes, please. So that was an example of autogenic inhibition. Oh, there is a clap icon. That's fun.
No. Here.
Thank you. Bam. So that's an example of proprioceptive neurofacilitation, which is like the technique to stretch someone's muscle. In this case, we were doing hamstring. But what it is we're utilizing the autogenic inhibition reflex. It's a reflex that if you take a muscle and it is being contracted by too much of an amount, it reflexively starts to turn off. Then that's to prevent ripping of the muscle. Any questions, guys? No questions? Perfect. Okay. Now, the main reflex that we all know about is the tendon tap reflex or the phasic stretch reflex. Do you guys remember that? Tendon tap reflex at the medical doctors? The knee one, yep. The knee one, yep. That's true of all muscles. But what happens is that if a muscle is contracted too quickly, the muscle spindles register that it's being stretched or lengthened too quickly, and it fires to, it's a reflex that fires from the spinal cord to get that muscle to reflexively contract, to pull back from the quick lengthening. So when you do the tendon tap reflex, you tap on the tendon, and then it obviously pulls the muscle very quickly, and so it reflexively contracts back. I can show if I'm breathing again, if you guys want. Yeah? Okay. Hey, I'm breathing though. Sorry, I lied. Do you have a reflex hammer? I don't know what term it's in. I thought it was in the. Sorry, guys, I'm just getting my reflex hammer. I think it. Oh, I don't know what it is. Crap. Okay, guys, sorry. I can't find my reflex hammer right now. But hey, it was there the whole time.
Yay.
Okay, so can you guys see? The high now? Okay, so it's there. Round 7. So with the reflex, you see? Okay. That's good. Okay. So with a reflex, what you're doing is you're tapping on someone's tendon, and then what you're doing is you're eliciting whether or not the tendon tap or the phasic stretch reflex is working or not. So let's say we're looking at her knee. So we want to look at the activation of her quad muscle. The hit on it. You see? So she's not doing that on purpose. Like I'm just hitting her knee and see how it's like. All right. You guys see that?
Thank you.
Ooh.
Yeah.
Ooh. Is that good? I need more. Yay! Yay! Yeah. All done. So why do you? So yeah, that's a good question, Carolyn. So what is the purpose of doing that? Like, do you think clinically? What can you guys think of as an example of why we would check the integrity of someone's neurological system by using the tendon tap reflex? So that is the patellar tendon reflex, and it's yes, exactly. It's to make sure that the neurons are working. If I did that and the reflex isn't happening, where is the problem? Yeah, it could be anywhere from the spinal cord or through the lower motor neuron. because the reflex goes from the proprioceptors going up to the spinal cord and then back out. So the problem would be in the lower motor neuron area, or the part of the spinal cord where the reflex is. Now, just like I said, in the brain, if we have a problem with the upper motor neuron, we get spasticity. So it wouldn't be a loose muscle. It would be like a very spastic muscle. So you can tell it clinically different. So when you do the stretch reflex, you're just checking the spinal integrity or the integrity of the neurological system in the lower motor neuron part. So you do it to say, oh, okay, like clearly something's up. You guys okay? We've got 10 minutes left. You guys okay, or you guys are all good? Okay. All right. So here's another example of the stretch reflex. That's just depicting what we just did. When you have a tap on the tendon, you reflexively stretch the muscle. It fires the muscle spindles, which gets a reflex to flex that muscle through the spinal cord back out to the lower motor neurons. Has anyone ever heard of this withdrawal reflex? So when we have a painful stimulus, you know when you touch like a hot pan, you immediately flex back? Or what happens when we step on something that causes, like a step on a nail? What happens? Yeah, yeah, we pull away. So Matt said we can't stand on it. Exactly, it's also true. A withdrawal reflex is a reflex that's as a result of a painful stimulus. And so what happens is that when there is a significantly painful stimulus in one of our limbs, it reflexively activates the flexor muscles of that limb. So when we step on a nail, we reflexively flex the muscles of that limb, and that withdraws the limb from the site of pain. When you grab a hot pan, you immediately flex away from it. You're withdrawing your limb from pain. And then you would look at it, correct. Different reflex, but yes, that's correct. So with the withdrawal reflex is the activation of our flexor muscles as a result of a painful stimulus that happens through a reflex in the spinal cord, right? So that way it's not like, oh, I just hurt myself. Like it doesn't have to go up to the brain, process, oh, I hurt myself, better move my arm. It's a reflex that quickly happens. Then, right? How many times you hurt yourself? You already moved and looked at it before you even registered that you hurt yourself. Because those reflexes happen before we perceived. Now, when you get a painful stimulus or a withdrawal reflex in one of the lower limbs, you get a reflexive cross extension reflex. So if, let's say with like when we're talking about with Matt, if you step on a nail and you automatically withdraw your foot from that pain, you have to put your weight on the opposite foot or else you would just fall onto the painful stimulus. Let's say you're walking, like you step on a burning like coal, right? If you're gonna withdraw the foot that you stepped on, but if you didn't put the weight on the other foot, you're gonna fall back onto the painful stimulus. So what happens with a withdrawal reflex, when it happens in the lower limb, is you get automatic reflex of an activation of the extensor muscles in the opposite leg. So in that reflex, what happens is that you get flexion or withdrawing of the painful leg, and then you get your extension or the weight put on the good leg. So with the withdrawal reflex, you get automatically a crossed extension reflex. You get a crossing of that reflex to activate the extensors of the opposite leg. And then when you want to look at it neurologically, of what it would look like in terms of the inner neurons in the spinal cord, it would look like this diagram here. Are you guys okay with that? Yeah, it's definitely, and so so Apollo says it's so intricate and it's all just connections, right? The neurological system is just signals being sent, but what makes our neurological system able to do what it does is that everything's interconnected, and specifically with inner neurons, everything's causes contraction of other stuff, or right, like so when we looked at for every motor neuron, you have 10 sensory neurons, you have 100,000 interneurons. The big key in our neurological system is inner neurons. Everything is like wired together in such an intricate way that we're able to have one thing affect so many other things. We have so many more interneurons that allows for what we see in terms of our ability of our neurological system. Cool? So now we're just going to finish off with the upper motor neuron tracts, and it's not as complicated as the sensory tracts. Okay? Can I continue on, everyone? Or is there any questions? All good? Okay. So the upper motor neuron tracts, and so remember, tracts are the sort of groupings in our white matter that are the collections of the neurons that are going to be going up to our brain or down from the brain to the spinal cord. Do you have a specific question, Sahar? Oh, okay, right. You don't no questions. Got it. Sorry, makes sense. Sorry, follow along. Okay, so with our upper motor neuron tracts, they're going to be divided up into 3 different classifications based on anatomical location. We have our medial upper motor neuron tracts. So those are going to be the tracts that are located more medially in the white matter of our spinal cord. And that's for specifically innervating our postural and girdle muscles, so our core muscles. We have our lateral upper motor neuron tracts. Those are going to be the groupings of the tracts that are located more laterally in the white matter, and that's going to be used for activating our muscles for fine control or intricate movements. And then we have our anterior non-specific upper motor neuron tracts that are anterior, and these are going to be used for neuromodulation or contributing to background levels of excitation in the spinal cord and reflex arcs. Okay? I promise you they're not as complicated as last day's tracks. But again, the best way for you to sort of study or organize them would be to get a sheet of paper and then to sort of group them out. So we have our medial upper motor neuron tracts, and there's 4 of them. We have our lateral upper motor neuron tracts, and there's 2 of them. And then there's the anterior non-specific upper motor neuron tracts, and then there's 2 of them as well. So let's first go into our medial upper motor neuron tracts. Now, medial upper motor neuron activity is involved in controlling our posture and gross movements, and it's typically done without conscious effort. So remember, when we activate our muscles, when we do a voluntary movement, we first activate our axial muscles, our postural muscles, to stabilize our body through the premotor cortex. So it's done before voluntary movement. The 4 motor neuron tracts, upper motor neuron tracts that are sort of like involved in that are located on this slide here. So we have 4 medial upper motor neuron tracts. These 4 tracts are going to be utilized for activating our core and posture muscles in response to different stimuli. The main tract is the reticulospinal tract. And what this does is it facilitates the activation of our posture and girdle muscles. So it's the baseline activation of our posture muscles, okay? So it's coming from the premotor area. And so remember, when we do a voluntary movement, we first contract our core muscles to stabilize our body. The way that's going to be sent out to because you're unconsciously activating your core muscles, it just kind of happens. The tract that sends that information out to the posture muscles is the reticulospinal tract. Okay? The medial vestibulospinal tract, so vestibule means the vestibular, like your inner ear for equilibrium. The medial vestibulospinal tract, this tract is going to send information out to the core muscles of our neck and upper back based on head position. So remember that with our neurological system, sensory information in terms of our vision is our main priority. So we put vision information above, or make it as a priority above everything else. And so it's very, very important for us to stabilize our head and make sure that our vision is like the best. And so if you look at the difference between, this is another slide, a study, they looked at the difference between Major League Baseball hitters versus amateur ones, or even semi-pro. The difference in sort of their head positioning is considerable. That the biggest difference is that people that are pros, there's such a minute movement of their head during their swing, which means their eyes are able to really figure out where the ball is coming from. So our body puts a priority on stabilizing our head. And so rather than be like, okay, I'm tilting to the left, I'm looking to the right, better activate my trap in this way, there's a reflex that does that through the medial vestibulospinal tract. From our inner ear, we can sort of figure out, or the body knows which way the head is positioned, and then it will activate our neck and back muscles to make sure that our head is always stable in whatever position it's in. So that's the medial vestibulospinal tract. The lateral vestibulospinal tract, also coming from the inner ear, what this does is it responds to activating our muscles when it realizes that we're standing. So it responds to gravity. So have you guys ever heard of the idea that like, or like, has anyone ever been on the subway and you can still fall asleep even though you're standing? Has anyone ever fell asleep standing up? Right. How can that be? You're asleep, so shouldn't you just fall? 9:15 bucks. Okay. The reason why is because of the lateral vestibulospinal tract. When we stand, our inner ear registers that gravity is now down, we're not lying down. And so there's a baseline activation of all of our extensor muscles in our back and legs to keep us standing. So that's another level of activation that's taken away from the brain, or processing that's taken away from the brain. It's a reflex via the lateral vestibulospinal tract. And then the last tract, the medial corticospinal tract, it is coming from the cerebral cortex. So it's something that we're consciously aware of. And so this is when we consciously, like, you know, when you're like trying to like look good in like a picture and trying to flex your abs, that's when we consciously flex our core muscles. It's a core muscle, so it goes through the medial, it goes from our brain out to the muscle via upper motor neuron down to lower motor neuron. It's going down via the medial corticospinal tract. Michael says, so we don't really need beds. Well, it's not safe, because then we're always having to like sort of be semi-awake to respond to any perturbations and stuff. So no, I mean, it puts us at risk if we all sleep upright. But yes, I think the other thing too is that your body needs a break, right? Sleep is supposed to be restorative for everything. So the medial upper motor neuron tracts, they're called the medial upper motor neuron tracts because they're upper motor neurons, and the tracts are medial or middle of the white matter, and they're responsible for us activating our core muscles. From the premotor area and from the brain stem, for the baseline activation of all our core and posture muscles, is through the reticulospinal tract. So that's the activation of our core muscles subconsciously in response to the movements that we want to do. The medial vestibulospinal tract is the activating of our neck and upper back muscles based on how our head is positioned to make sure it's stable. The lateral vestibulospinal tract is the activating of our extensor muscles in our back and legs when we're standing. And then the medial corticospinal tract is for the voluntary contraction of our core muscles. Okay, so this is what we use, the medial upper motor neuron tracts, to activate our core muscles. Is everyone okay with that? Awesome. Okay, so this is an example of what they look like. And that means our lateral upper motor neuron tracts are going to be the tract that is utilized in activating our muscles for fine control. So not core and postures for voluntary movement of like our fine, intricate movements. We're going to use our lateral upper motor neuron tracts. There's two main tracts. There's the lateral corticospinal tract, which is the biggest tract of our body. And then we also have the rubrospinal tract. Sorry, the largest tract of the motor tract. And then we have the rubrospinal tract, which is not really utilized in humans. So two different tracts, and they are responsible for doing fine control of our muscles. And that's called fractionation. Our ability to do fine control with our hands and our face and our limbs is through selectively activating individual muscles, or fractionating our response or our activation of individual muscles. That's called fractionation. Okay? And so the two tracts are the lateral corticospinal tract and the rubrospinal tract. The lateral corticospinal tract is the one that we typically use. It's located laterally in the white matter, and it goes from our primary motor cortex. Remember, the primary motor cortex is for the voluntary contraction of our muscles for fine control. All that information, let's say I want to pick up this cup, right? That's going to start as activation in our motor planning areas and activate my core muscles. But then the fine control movement, the voluntary control, is going to go from my primary motor cortex down through my brain stem and down the spinal cord through the lateral corticospinal tract to the spinal cord at the specific level, and then out to the lower motor neurons that go to my limb, in this case, my left arm. Remember, the pathway for our upper motor neuron, or for our motor neurons, is two neurons: upper motor neuron, lower motor neuron. The upper motor neuron comes down through the spinal cord in the white matter via the medial or lateral upper motor neuron tracts. The lateral corticospinal tract is the largest, and it's for voluntary control of our muscles. The rubrospinal tract is a lot smaller, and this typically goes to the extensors of the upper limbs. Rubrospinal tract was very big evolutionarily in four-legged animals. And because we're not four-legged, we don't really utilize it a lot. But it's there. It provides and facilitates extensor muscles of the upper limbs. And so there is the rubrospinal tract in the human spinal cord, so I'm bringing it up. Okay? You guys okay with that? So this is the medial upper motor neuron tracts and the lateral upper motor neuron tracts. Medial upper motor neurons are for core and posture muscles. The lateral ones are for voluntary control of our movements for fine control or fine movements. Okay. The lateral upper motor neuron tracts, they all are starting from the primary motor cortex. Remember the motor homunculus, which depicts where, or the graphical representation of what the neurons are associated, or what part of the body the neurons of the primary motor cortex are associated with what part of the body. And just to review, remember we have our motor planning areas. The premotor area is going to be responsible for a core activation, a core muscle and postural muscle activation. It's activated before voluntary movement. Now we know that the way it gets from the area out to the muscles is through the reticulospinal tract. Okay. Any questions, guys? I know it's a lot. These tracks are for neuromodulation. And so these are the non-specific upper motor neuron tracts. We have our raphe-spinal tract, which is the primary source of serotonin in the spinal cord. Does everyone remember what serotonin is? What does serotonin do in our body? It can be, but remember, serotonin was for our levels of like alertness. So when we're alert, we're more like, we're more alert. We move quicker. We do everything like we're alert, right? We're alert, happy, and ready to go. Whereas when you just wake up, you don't have a lot of serotonin, and so you're groggy. You move slower. This is for neuromodulation. So when we're awake, we have the raphe-spinal tract that releases serotonin in the anterior part of our spinal cord. And so neuromodulation, it gets all the neurons to fire. They're all alert, right? Okay. Now, the cerebrospinal tract is going to be responsible for releasing norepinephrine or epinephrine in the spinal cord as a neuromodulator in response to fight or flight. So do you guys remember when is it like you get in a car accident or something very bad happens, or you're stressed, and so your epinephrine is up, you feel very tense and the muscles are all ready to go? They're primed through the neuromodulation of our upper motor neurons, or sorry, of the lower motor neurons in the spinal cord via the cerebrospinal tract, which is responsible for releasing epinephrine as a neuromodulator into the spinal cord. So you can see that the non-specific upper motor neuron tracts are just for baseline neuromodulation in response to alertness via serotonin or fight or flight via epinephrine in the spinal cord. Okay? Okay, So the final slide of the lecture is just now talking about the different tracks that we've all talked about. So remember, I promised that at the beginning of sort of the lecture, or at the beginning of the course, that you would look at the map of the white matter of the spinal cord, and we would talk about and know what all of the different tracks are, or the groupings of the wires that go from the brain out to the body. Today, what we learned about is the lateral corticospinal tract and the rubrospinal tract. See how they're lateral in the white matter? Yep. Okay, I'll be right there. Sorry, guys, this went a little bit later. And then here we have the medial upper motor neurons tracks. See how they're more medial in the white matter? That's why they're called that. And these are for core and posture muscle activation. Awesome. So I'll, just to depict, remember next week we have a midterm. It's going to give, I would know this one. I can't remember what the other diagrams are. This is a good one. Okay. And it's going to be, remember, same thing, 35. I don't think I'm going to do a practice exam again. It's just to show you like the difficulty of the questions. Now that you have the experience from the first midterm, it'll be very, very similar in terms of difficulty. 35 multiple choice, and then 4 questions for, of short answer for 15 marks, for a total of 50 marks for the midterm. Okay? Any questions before I go, guys? Sorry for going a little bit over today. I just wanted to make sure we did a sort of the diagram with Ambreen just to make sure you guys sort of like got a visual. It helps understand. And then I will see you guys all next week. Have a safe and happy Halloween. And then I will talk to you guys soon. Okay?